Live from the Stability and Trim for the Ship's Officers podcast studio, where the vessel's its own best instrument of stability and trim. Welcome. This is William George. Hello. Your vessel is talking to you. Are you listening? I'm thinking of offering private stability and trim lessons using Zoom. My goal is to fill the gaps the license exam questions and the required license training does not cover concerning the management of your vessel's stability and trim. Would you be interested? If so, please give me an email at williamegeorge@gmail.com. Thanks a lot. Bye. Okay. This is podcast number 18. We're still talking about trim. If you have the book, we're on page 212. And this is actually something I was involved in with an expert witness case years ago. And it goes like this. The vessel is its own best instrument of stability and trim. This is a practical example of the LCG method. The LCG method will be used to determine the weight of the logs lost overboard from hatches number 3 and 4 during a voyage from Grays Harbor, Washington to Japan. Using the observed sailing drafts and known weights, determined the required longitudinal weight distribution to produce the observed drafts and the trim also. Determine the weight of the logs lost at number 3 and number 4 hatches. This can be calculated from the following observed drafts. The forward draft was 9.45 meters, the after draft was 10.44 meters, the mean draft was 9.945 meters. The trim was 99 centimeters aft. If we multiply the MTC by the trim, we get the trim in centimeters, 99 times 408.8, which is the MTC. We get a trimming moment of 40,471.2 metric tons. Then we divide that total by the displacement of the vessel based on its mean draft of 32,519.9 metric tons, and we get a trimming arm of 1.245 meters and an LCB of 3.985 meters forward amidships, which is denoted in the book by a negative distance. And the ship was trimmed by the stern, so basically the trimming arm goes from B to G. G will be toward the deep end. So the longitudinal center of gravity of the vessel, entirely loaded when it was finished, was minus 2.74 meters forward amidships. And again, we're denoting negative as forward amidships and positive as aft amidships in the longitudinal measurements. And there's a sketch here on page 213, and that's figure 9-10. It's a sketch of relative positions of the midship B and midship G, LCB and LCG. And note that the LCG and the LCB are measured from midships, where negative is forward and plus is aft of midships. Now, the interesting thing in this case is both LCB and LCG are forward amidships, but the ship is trimming by the stern. Why is it trimming by the stern? Because of the trimming arm. B is the zero trim position of the LCB, and G is aft of B, so what's going to happen is the ship will trim until B moves under LCG. And what we're doing in the picture here in the diagram 9-10 is we're just showing the ship as it was held in a zero trim condition. And if it was released to float freely, the ship will trim by the stern and B would move under G. So from the survey report, it's known that the ship did arrive in Japan with number 1, number 2, and number 5 cargoes on deck. By comparing the survey report photographs and the stowage plan, it does not appear that any of the cargo was lost from these hatches. It is now time to calculate the required weight distribution of number 3 and number 4 hatch on deck to produce the sailing drafts required as reported. We note here that the heavy oil and diesel oil that were reported on the vessel statements of facts, and this was done on this itemized list was done on figure 9-11 on page 214. So we have the observed sailing condition, which is the weight, the LCG, and the longitudinal moment. Now we're using the weighted average theory of moments technique. We're going to deduct the light ship moment, longitudinal moment, constant, fresh water, heavy oil, ballast, diesel oil, the cargo reported in the holds number 1 through 5, and on deck number 1, number 2, and number 5. And if we deduct all those from the sailing condition, we're only left with 3,908.66 tons total weight in number 3 and number 4, and a longitudinal moment required of 17,111.81 meter metric tons. So now, if we let X equals the weight of cargo in number 3 and Y equals the weight of cargo in number 4, as shown in the bottom of page 213, we can solve using simultaneous equations where X plus Y equals the 3,908.66 tons of cargo, and we know the LCG of number 3 was minus 10.32 meters forward amidships, and the LCG of number 4 was 16.88 meters aft of midships. So we can solve both of these equations, and both the second equation equals 17,111 tons, 0.81 tons. So we have X plus Y equals 3,908 tons, and minus 10.32X plus 16.88Y equals 17.111.81 meter metric tons. So to get rid of this, we have to multiply the first equation by the inverse number of, number 1, LCG. So we'd multiply 10.32x plus 10.32y, and then we'd multiply 10.32 times 3908.66, and then we can subtract the two equations, and we're left with just in terms of y, and we have to subtract the moments from the moments then, and we can come up with the value we see on page 214, where X is the cargo weight in number 3 hold of 17,90656 tons, and Y is the weight of cargo on number 4 hatch, which is 2,112.10 metric tons. These are the weights required to have the vessel float at the sailing draft reported when it departed. So you can use this LCG method many ways, but it's really powerful to use it backwards. And that's my message for today on this. It helps if you have the book, because this is not simple, but this is a case where if you were in high school and they taught you the classic solution of solving for X and Y, this is a practical application of simultaneous equations. Thanks a lot.